Witam wszystkich bardzo serdecznie na kolejnym webinarze serii No Fluff Jobs Masterclass. No Fluff Jobs Masterclass to kurs przeznaczony dla deweloperów, którzy chcą podnieść swoje umiejętności, dla wszystkich seniorów, którzy chcą wejść na wyższy poziom i poznać wszystkie te rzeczy, które każdy senior powinien znać, a które zna niekoniecznie, nie z tego względu, że nie chce ich znać, a ze względu na to, że nie miał okazji się z nimi zetknąć podczas swojej praktyki zawodowej. Dzisiaj ze mną jest Cliff, jeden z mówców w No Fluff Jobs Masterclass. Mogę śmiało powiedzieć legenda świata IT w Stanach Zjednoczonych, jak również legenda community javowego. Będziemy rozmawiać o debugowaniu wyścigów danych, data races. Jest to niezmiernie ciekawy temat i nie mogę doczekać się na prezentację Cliffa. Przy okazji chciałbym powiedzieć, że każdy uczestnik tego webinaru otrzymuje 20% zniżkę na kurs No Fluff Jobs Masterclass, także zachęcam do dołączenia, zachęcam do zapoznania się z tą porcją wiedzy, którą mamy dla Was dzisiaj, po to, żeby zobaczyć, co czeka Was w Masterclass. Jest to niejako taki przedsmak tego, co kilkuset zapisanych uczestników na kurs Masterclass otrzyma. I cóż, chciałbym teraz przejść na język angielski, nasz webinar będzie się odbywał w języku angielskim, także przywitam Cliffa i pozwolę mu zaprezentować ten jakże interesujący temat. Okay, good evening everyone. Let me switch to English right now. It's a real honor to host Dr. Cliff Click. I will not exaggerate when I will say a legend in the JVM space, a legend in the IT computing space. In the United States and in the world, and we're really looking forward to the presentation on debugging data races. Welcome, Cliff. How are you doing?
Hi. Yeah, doing great. It's all early morning, mid morning here, and very pleasant.
Yeah,
looking forward to it.
Perfect. Thanks. So, without any further ado, I will pass the floor to you, Cliff, and we're really looking forward to your interesting lecture. Good luck.
Thank you. Thank you. Hi. So yeah, I'm Cliff Click. I'm here today to talk about debugging data races. So I'll throw up an agenda for a second here. But basically, data races are one of the hardest problems people have to go debug. And so I'm going to step you through what one is, some of the common failure modes, common ways people write them. And then we'll get into some debugging techniques, how to solve for a particular data race. And then some Q&A and testing for how to solve for finding them in bulk across your code base. And we'll wrap it up. And there's a chat, but I only do English. So if you have questions or you want me to slow down or repeat something, that's all great. Throw it in the chat in English. Okay, so what is a data race? So I'm going to start by assuming we've all been coders for a while. We're all pretty senior here. So I'm going to show you some examples. You have to imagine, because it's all being done in short, quick order, so there's not a lot of time to do a deep example here. This code I'm showing is a little bit of C code from the insides of Hotspot from 15 years ago. And I inlined it a bunch and I simplified it a bunch, but the code looks something like this. If some method has some JITted code, or if it doesn't, return false. If it does, get the code, do a little setup, and then go execute the JITted code. And then occasionally, despite the check that happened, I would throw a null pointer exception in C code, which was a crash and burn of the JVM. I've debugged dozens of slight variations. There's papers which people explore variations of this kind of a theme as a fail. It's a fairly common fail, and it's not at all obvious what's going on. And we'll come back to this when I've talked more about what a data race is to show you what's really going on under here and why it fails. Okay, so what's a data race formally? Two threads accessing memory at the same time. One is writing, and there's no ordering intention thrown in by the user. But informally, it's really just you try to use more CPUs to run faster, and because one CPU is too slow, into frequency scaling, you had to use more CPUs to do something. So let's talk about it here with a picture. I call this a train track model. It's two timelines, and we're going to step through them in time order. But the data race is two threads, and they're accessing the same memory. They're reading and writing this code variable, and one of them's writing, and there's no language ordering going on. This is C code on the left here. I haven't declared anything volatile or not or atomic or whatever. And occasionally it breaks, and it breaks if You read it once and you test it and it was not null. The other thread writes a null and then you read it again, getting a null, and then you do something with a null and boom. So it's only broken if you're in between, which means if the code execution of setting to null, because setting code to null execution on the right-hand side, thread 2, happens before or after the 2 reads in thread 1, no crash. So you might get this very rarely in testing, but you might get it more often under heavy load. We get a lot more context switches. And in my case, the crash was fairly routine in production and never on the desktop. So never under the debugger, never on the desktop, all the time in testing.
Which, can I have one question? Can you just explain the audience what a context switch is, so that they...
Okay, so this would be when you have one core having more than one thing to do, more than one thread for one core, and the core flips back and forth between 2 different pieces of code. All the time happens on one core machines. Even with multi-cores, it's typically the case that one core will be responsible for multiple threads, and you'll get this back and forth execution all the time. Anytime you've done a container or a Docker or whatever, and you've crunched this machine down to one core, as is common on cloud applications where you have a low frequency, low cost processor running, it'll have multiple threads to go do things, of which it'll flip back and forth. If the flipping timing, which is not in any way guaranteed by the OS as to when it happens, if the timing is bad, you die.
Thanks.
Yeah. Okay. So when and why can I have loads and stores? Did I get this right, or I missed one in here? No. Okay, fine. So when and why can loads and stores move around and get reordered? So it turns out the compiler all the time moves code for scheduling purposes. It's to cover latency for cache misses and the like. It makes the code runs faster. The hardware also does the same moving, again, for speeding up things, typically cache miss costs again. And this motion's allowed unless you explicitly deny it by using, volatile or lock in Java, atomic, and C++. And you obviously need 2 or more threads. And you require ordering on all the threads that are involved, not just the writing thread. And it's sort of a common mistake people make is to think that if I only have ordering on the writer and not on the reader, can I fail? So let's look at this here, and I'm going to run this train track again, but now doing sort of kind of like a double check locking thing. Thread 1's going to initialize some field with good stuff, and then set in a init flag saying it's done. And thread 2 wants to test the init flag, and if it's done, he's going to get the thing. And if it's not done, he does something else. Maybe he takes a lock and tests again. It's double check locking, but it doesn't have to be. It's just the general notion of filling good data, setting a flag saying it's ready. Okay. And so can these loads and stores be reordered? And then, yeah, the compiler will just reorder them because there's no other ordering going on. So thread 2 just reads the data field, and it's not initialized yet, so he gets junk or null. And then he reads the flag after it is initialized, and you're dead. Suppose I don't reorder them in the compiler, but it turns out the hardware can reorder them. So here I've left them in order, in code program order, but the compiler, the hardware executes the load of init, and that might miss in his cache, and the data might not be ready for a long, long time. So he goes ahead and speculatively executes loading the data as the next instruction. It's all speculative, so if you abort because the init's not set, you abort it, and it's great. But in this case, eventually a init gets set, so he picks it up much later than the read of the data, says it is true, his speculative switch correct, so he keeps the null data, and you're dead. So you have to have a reorder on the reader side, and you have to have a reorder on the writer side. So here I've thrown in membars as an example to show where I've prevented reordering. And the membar is to prevent reordering for both the compiler and the hardware. On some hardware, the membar might be an empty thing, a line in the sand, but the compiler has to know that it's there because he's preventing that reordering. And on some hardware, it's an explicit instruction. It varies by hardware. So, an ARM chip on a phone here might put an instruction where an x86 would not, but there is an ordering point. So if I instead claim I'm only have reordering, no reordering allowed on the reader, and only on, on the writer, and on the reader I am allowing reordering, well, we just did this a second ago. It's the missing load ordering, and both the hardware and the compiler can reorder. It doesn't work. Turns out if I do it on the writer side, but I allow the reader to reorder, I can still fail again. I'm sorry, get this the correct way. The writer is going to reorder and the reader is going to be in order. the writer can write stuff, it will miss in cache and not be visible to the second core that's running T2 till a long time later. And then he writes init, which for whatever reason gets to the second core faster. And that's because the hardware doesn't make any ordering guarantees of multiple unrelated stores as to when they're visible on other cores. And so again, thread 2 reads the init that he just gets quickly. He then membars himself, which prevents him reordering his loads. He then reads data fairly quickly. It's not yet set. He gets a 0. Then data becomes visible later. Some hardware will not do this. Some hardware will. It varies by hardware. You have to have an ordering, or else on the different hardware, it will fail. Fine. So that's enough about what is a data race. So let's go down to some common ones that people write by accident all the time. So by far the most common data race is a double read with a write in the middle. And this would be where you read a field P and you test it against null. And because it's not null, you then call p.field to go look up something inside of P. But now P is null and you crash and burn. You can also get it with 2 writes and a read in the middle. This is an example where I have, for instance, an array list. It's doubling in size because I've appended something to it and it got bigger. One guy's busy doubling it, and so he doubles the size field, and then he allocates a new array of twice the size, then he copies from the old to the new. Great. But he has 2 writes, one of write of size of double size, one of array of double size. The second thread's getting the last element. He reads size of the new double-sized thing. He reads the old array, which is not yet doubled. His length is out of bounds. He throws an array index out of bounds exception and dies. Fine. If you're in C, instead of getting an array index out of bounds exception, you just walked off the end of the array and grabbed some junk from memory. It's just junk, and you don't know what you get. Double check locking has another fail. It's similar. We'll go into a little more detail. But the key thing here is that you read a global to see that it's null or not, because you know you're going to only allocate it once. You're going to initialize it only once. You're going to have zillions of readers who want to have low latency. So the readers want to be quick. They just want to grab the damn global, see that it's not null, and run with it and be done. No synchronization at all. In particular, you do not want to lock all the readers because they're locking against each other, and then they can't make forward progress because they're all trying to get the damn global. Fine. If the global's not set, the first man in takes the lock, tests again. It's still not set. He sets it, and you're done. But it's locked, so it should be good, right? Wrong. Let's watch the fail here. So thread 1 has already tested, locked, tested. It's still not ready. He's writing it. So he makes a new object into some register R1. He stuffs some good data into memory that you want to, that's your initialized thing. He then publishes it by writing it to the global. Bad luck for him. His write of the field misses in cache. It's slow going. It's going to be a while until it gets there. And by the way, that write missing in cache is pretty much 100% guaranteed, because the new only gives you memory that has never been in your cache since the last GC cycle. So pretty much that write to field is 100% guaranteed cache miss, several hundred clock cycles to execute. Whereas the global got tested repeatedly by thread 1, it's almost surely hot in his cache. So it goes right away. Then thread 2 runs along, reads the global. It's, for whatever reason, it's quick for him to read it. So he reads field, that's now slow. It's uninitialized memory. He gets the wrong thing. Then the write shows up later. Then you unlock, including a memory barrier, and you fail. Okay, what happened here is the unlock exists. It's in the wrong place. It's after both writes, not in between the writes. So whether or not the reader is ordered or not, the writer has to be ordered, and the writer has no lock between his writes. And that's the fail. And of course, you make global volatile. We should all know this by now, and that's, that solves the problem. Okay, let's look at the double read again, because this is a more interesting fail. The fail here is that you've read it once, tested it, and then you read it again, and it changed. Fine. The compilers like to run an optimization called common subexpression elimination, and that will work on 2 loads of the same thing twice and common them together and just do the load once. And if there's only one load, there's no bug. You load it once, you test it for a null, it's not a null, you use what you loaded, that's not a null, and you're good. Fine. So in a C compiler, you might crash into debug build, but not in a product build, because the optimizers kicked in on product. In Java, the optimization kicks in and when load hits. So just as load begins to hit the system, things are still interpreted, but you have a lot of context switches for a lot of heavy load. And because they're interpreted, you have two loads, the interpreter's doing them both. After the jitting's done, you only have one load because the JIT has done just what the C compiler JIT does and comments them together. So if you survive startup, there's no bug. You might live a long time. But right at startup, you might crash and burn for having this kind of a racy data race. And therefore, you have this funny situation where the server sometimes crashes right on startup, and you're really annoyed, but no one's using the server yet because it just got started. So you kill the damn server process and you restart it, and you kill it, restart it, and suddenly it sticks and it works. It's all good. The server's up, and you walk away and say, "Holy crap, I'm done." And so the bug might live around for a long time as a really annoying, hard to catch thing that only crashes right when you start the server.
Okay, can you recap this? This is a very interesting takeaway. So it just means that because the compiler optimization or like the runtime optimization will kick in later,
it removes the bug.
Yes, the bug will appear at the very beginning. It may appear at the very beginning, and it will never appear afterwards because this is one load. That means that, like, if we don't hit the bug at the very beginning of the runtime, then we may never actually experience it. So it makes the debugging very, very hard.
It makes it hard to debug. Yeah, right.
Okay.
Now, there's no guarantee that the compiler will inline them here. So you're not guaranteed that the JIT fixes it, but it is common the case that the test and the use are near each other. So it's commonly the case that the JIT picks it up and removes the bug. If they're far apart, the bug's more obvious. It doesn't go away. And as soon as the JIT kicks in, code runs a lot faster. So the repeat rate of load it once and test, load it again and field, load it, test, load it, field, happen a lot more often after the jitting's done. So if they don't get commented up, then the bug becomes more obvious. But if they get commented up, the bug went away.
Exactly, and that's exactly why we think it's so essential to understand the internals, because at the very, on the surface, people may think, okay, it's not that interesting what the compiler actually does behind the scenes, but as we see in this example, it's actually essential to understand what happens to identify the behavior of the bug in this particular example. So thanks for
and like I said, I think this is the most common bug people write, and I'm going to get to it in a minute of why you write it by accident more commonly than most other things here. Okay, but I have the slides are set up here. I'm going to talk about HashMap for a minute as the other semi-common one that I've saw a number of times. And this is the HashMap has this common use case where you have a rare writer updating a table and many readers. And because you're using HashMap as a cache, and the cache is working as caches hope to do, and most of the readers hit in the cache, fine. Because you're mostly reading, you would like the readers to be fast, so you make it unsynchronized. This was speed hacks from years ago, but similar things with the same kind of speed hack thinking, I keep seeing on and on and on. So this is a common thinking problem. It's not necessarily done with HashMap. So you want it fast, so you don't synchronize for the readers, but that means the readers catch half a writer occasionally, and they'll blow out a null pointer if the writer's mid-write. And you know that, so you go ahead and catch a null pointer exception, and you just fix and retry. But you can be middle of a resize, and I talked about it earlier, where the size doubled, but the array hasn't yet been doubled, and you get a double size table, and you crash and burn for that one with an array index out of bounds. But there's a third fail mode that is really insidious. And this is a case where, for whatever reason, you're resizing the table, and readers call size, and size can decide there's too many reprobes and resize the table. So now the reader is writing the table to resize it, but he's not synchronous. So another reader can also resize the table. And in this case, if they don't throw an array index out of bounds and don't otherwise crash, it's easy for the linked list in a hash map to get corrupted. So if you have a ties on a bucket, you get a linked list chain, they chase down. So they hash to some array entry, and then they chain a linked list. Great. Linked list should be short. That's a hash table's purpose, fine. But if the list gets corrupted, it can get cyclic. If it gets cyclic and you go probe it, you run to the end looking for a hit, except there is no end because it's cyclic. So you're just running in a circle forever. So if this is done inside some large fancy web server, you might have a transaction that times out. And then the server wants to retry. Now the thread that's in the linked list, he's stuck running forever, just chasing a pointer, never getting to the end. So the web server launches another thread that tries the same transaction. Well, he hashes to the same slot in the same table, gets to the same cyclic linked list, and he also gets stuck running forever and never getting through. And slowly at timeout speed, by timeout speed, a new core gets launched into the cycle and stuck there. And they're all stuck there, and your server's throughput slowly grinds downhill as timeout by timeout, all the cores get burned one after another, chasing the same linked list forever, never getting done. As soon as you blow the server down and restart it, the bug went away because you rewrite the table on reboot and your server's back up and it's normal again.
Yeah, and
but
it's a great kind of takeaway that like a call to size may actually internally resize the data structure, which is a mutation which we're not actually expecting. We're just expecting it to check like an end value or volatile end value, and that may cause actually the whole server to eventually go down in a way that it's actually very, very tough to debug, like looking at the logs. Oh, the transactions are timing out, what's happening, and it's just kind of like a corrupted linked list, So
yeah, it's really, it's very hard to debug these things.
Yeah.
Okay, so so enough with common ones. Let's go look at some techniques here about how to go chase things down. And I'd love to say I have a silver bullet and you do this and it works every time, and I don't. I have a variety of things I do. I use them all at different points. They all cover different kinds of data races and different difficulties of the problem. And between them all, I typically get good enough coverage to chase things down and get things working. So they're in broad topics. They're visual inspection, that code review, right? It's very slow. It can be very accurate. I want to say state of the practice because you wrote this code, the code's now buggy, and you look at the code, fine. Printing, which has a problem with it because it changes your timing, can hide bugs, logging things, right? I have a better printing solution. This is very point specific. It's a heavyweight technique in terms of you have to write a bunch of code, but I've never had it fail, but it is kind of heavyweight to go use. So we'll talk about it in a second. Static analysis tools, mostly not useful, except I'll recommend Find Bugs, but it's actually, there's a commercial follow-on version of Find Bugs that's substantially better that I can recommend because I've seen it work in practice at bulk at scale. Fine. So visual inspection, easy to get started with. It turns out you don't have to have the code because you can inspect core files, which I had to do repeatedly with looking at the VM itself, which is a C program, and I got core file dumps for people. Ugh. It's very slow. Sometimes you can make directed searches where because I saw this test, therefore that has to be true, and because of this, and that has to be true, because this must have happened, then this, and you play this detective game, this Sherlock Holmes game with yourself, trying to puzzle out what's going on, and you have to be a memory model expert and a domain expert at the same time, and so it doesn't scale. It's very difficult. That being said, it's really easy to get started with. People do it all the time. The biggest problem you typically have is you don't know the players, and by the players I mean the set of things that might be shared, like my hash map where the reader calls size and the size calls resize and the reader becomes a writer, and you didn't realize that when you started, right? If you're maintaining somebody else's code, it's often the case you don't realize what's a shared variable and what's not, or when threads or which threads can touch and modify the variables. So it's very helpful to make the players obvious by using large flashy comments. Another one is annotations are really useful here to say, this variable as an annotation is supposed to be under this lock over here under all its uses because tools can do them automatically, but people can look and see that it is or is not following the algorithm designer's expectations, right? Okay. Here's more on the double read, and this is where people typically fail on this one because they use an accessor to give meaning to a complicated problem to the variables in question. They have something like an isReady, and they have a go get it accessor. And the problem here is isReady reads a variable, and the get reads the same variable, but they're not called the same name. They have different names here. And so you hide the fact that you've read it twice. And if once you've read it twice, there's the chance for the writer to come in the middle and you get screwed. You need to change your access pattern to read a flag and the value in one shot, typically by declaring the value has a particular instance of it, which means it's not ready, which is usually null, but it doesn't have to be, but it is usually null. And so you can get the thing, test for it being ready or not, and use what you got. So the main thing here is that every load and store is basically part of some algorithm, and they have to be explicitly inspected to make sure that you're getting it right. And the usual pattern that works is you have to get all the reads in a row of everything that you're interested in testing all at once, then test them all, and without ever loading them again, do whatever update you're going to do. And almost always any other pattern here where you get and you update and you get and you update allows an opportunity for somebody to change something on you that you didn't understand and leads to a crash down the road.
Yeah, that's a great example, and just to mention one kind of like war that sometimes happen in in teams, because some people say, oh, it's not really that super object-oriented programming because we are like using this extra variable, and I have this super cool method is ready and get, and I encapsulate the internal. And this is a great example that it's you have there has to be some balance in there, but some people are like biblical about some of these things. So
I'll push more on this very topic and a little bit later in the talk here, because
Great.
there is a coding style change that has to happen to use concurrent algorithms.
Yeah.
And you kind of want to separate it out from your business logic. And so there's some thinking that has to be done there to say, yes, the business logic is very nice, and I love to have my accessors to think about it as a business level. But in a concurrent algorithm, it's also important to know exactly what I'm touching and when and where. So we'll talk about that when I get to it.
Awesome.
Okay. So there's another thing people forget when they're using visual inspection here, and that's what I call a cycle. And so when you're thinking about writing your concurrent code, it's doing something, you have some sort of start, and I did my thing, and an end. I locked, I updated the variables, and I unlocked. Okay, fine. And you're carefully expecting two guys lock and unlock and the end to do. You look at it carefully, but really the code's in a cycle where I started, I did, I ended, I did something else, I came back around, I start, I did, and I came something else, and I'm running this endlessly in a cycle, maybe a million times a second. And so I'm not necessarily looking at something doing an end where I've unlocked, did something unrelated, and then I relocked and started again. So I have a chasing each other's tail point where you've got to look at the flip side of the cycle. And here's a railroad track where I'm showing where endlessly threads are doing something like read a variable, test it for null, read a variable, execute it, flush, set it to null, read it, test it, test it, null, read, test, blah, 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 blah. And you have to look at all the possible interleavings. And the last one down there is actually the double read write, where I read it, tested it, got a flush in, read it, and died. Right? But did you see that in the infinite stream that went by? You got millions and millions of them? No. You have to put your head around there is a cycle, and you have to check all patterns of the cycle against each other in all directions. Okay, let's change to printing. So printing, logging, events, you make noise at every read and write of the shared variable of the problem you're trying to debug. And then after the crash, you inspect the trace, right? The problem, of course, is that printing serializes results, and you have IO, which blocks, which changes their timing, which hides the bug. And I totally had many, many bugs where they would never, ever debug in the desktop, in the debugger, or even as I added more and more logging to get closer and closer to the problem, the bug got hid more and more and more away from me, right? And then, that one, the middle one there is what you see is not what you get, even on standard out print line, print stream, because the OS can buffer per thread. And you get this well-known Heisenberg thing. Okay, what do we do about it? So I have this hack. And what I'm going to do is I'm going to make printing cheap. And when I say cheap, I'm going to get it down to a couple of clock cycles cheap, like nanosecond short cheap. And because it's so cheap, the odds of it breaking a data race diminish down to almost nothing, and I can use it to catch almost every data race here. So the way to make it cheap is I write event tokens to a per thread ring buffer. Okay, a lot of words, so break it down per thread, because I can't have contention across multiple threads. Each thread is its own independent thing, no locking or blocking for a thread. Tokens, because I can't do strings, because strings cause allocation. And as soon as I do allocation, I get cache misses, and they're expensive. So I cannot afford to do any string creation at all. You can't have quote, and here I made it to this point. Cannot do it. It just, maybe you got a constant string and didn't allocate, and maybe you got an allocation and you're screwed. So you need a token. It's a ring buffer because I don't need an infinitely, hang on, I don't need an infinite size buffer. I'm just going to step it forward and wrap after some time. And how much some time is varies by the problem. Typically a few thousand is good enough. So you had a question, Tarek?
Yeah. So what do you mean by token? Just the object you want to kind of output?
Not even an object, literally an int. So I do the C thing that you do in C programs all the time, where you have a table of ints. I say const final int x equals 0. Event 0 is equals 0. Event 1 is 1. Event 2 is 2. It's stupid. It's painful. It sucks. And associate them with a string. You can use a Java enum if you put the value that gets assigned to the enum, not the enum itself, which is now, as a Java enum, it's an object. You don't want to put any objects in the ring buffer either. You literally want to have only ints. As soon as you put an object in the ring buffer, you need a store barrier as part of the code generation. You have ordering issues. You want only an int. There's one other int you have to have in there, and that's because you have to have nanotime, because you have to have ordering, but you have to have ordering across threads. And then you have to look at this thing after the crash. You have to post-process it now. So you grab all the ring buffers from all the threads and you sort them by nanotime, and then you can do a printout. And it turns out that it used to be the case that nanotime was not coherent between cores on the same die even. In which case you have to have a smarter sort that has coherency events that you threw in as events that superseded nanotime, and then you use nanotime when you didn't have other ordering. It's a little more complicated to do your compare-to relationship, but once you get it figured out, it sorts pretty easily. And then you look at you have a timeline now. You look at the crash. Oh, the other thing you do with those ints is you reverse them to some pretty string that you can fucking read, right? It's hard to read the damn int, so you don't. And you get a timeline, and the timeline's almost always, it points out who done it, where it happened, what the bug was. I've done this a handful of times, say 5 or 10. Every time it's caught my bug. I've done it between cores. I've done it between nodes in a clustered computing situation. I've done it sort of anywhere I have racing things or I have timing bugs. It's heavyweight. It works.
And just to understand, so you store the int, like with the code kind of where you're logging, and you also store the nanotime afterwards. So you store
in the same ring buffer.
Okay.
Yeah. So usually I have a call that I make that's debug.dump or log, and I put a token passed in, and it can be the enum at that point or a string even, but the logging event itself does something really cheap to do the logging. Actually, I can't even do a string. I tried doing a string once. That didn't work. I had to do a token there. It has to be, I can't do any lookups even at that point if its timing's that tight. If the timing is kind of loose and the bug's not going away, you can get away with being a little more easy to read, but you can drive it down to 2 nanoseconds, basically, test the ring buffer for wrapping, store an int, read the nanotime, which is the read TSE register. It's a single hardware instruction, a couple clock cycles, and store it down. It gets really, really cheap.
And it's just kind of like worth to mention why it's a ring buffer, so that it kind of wraps around and there's no location in between, right? So we just kind of
there's no blocking. Yeah, if it's not a ring buffer, it gets full. What do you do when it's full? The usual thing is you write it. Well, now you're blocking for IO. So there is no full in a ring buffer. It just wraps. Yeah. So if your crash was triggered by an event that happened much earlier, then the ring buffer is not big enough, and you have to size the ring buffer big enough.
Yeah.
But if the crash is tight such that you can't do any blocking at all, typically it doesn't require that much in a ring buffer, and you don't put events everywhere. You put them where you think you have issues. So I typically make a ring 1000, 1024, power of 2, because I'm doing an AND function for wrapping. I don't even test for AND buffer. I just AND mask and wrap that way.
And is there any kind of ready, like, I don't know, like a framework that does it, or you just code it by yourself?
I've only done this, a dozen times. So I typically write it from scratch the first couple. Once I have it in a particular project, I just leave it in the project and I pull it out, as needed. Usually changing the event tokens for the debugging question, but leaving the wrapping and the sorting and things like that, that all just remains.
Yeah, that sounds.
And the other one was calling it when I detected a crash event by default, so that after this kind of a crash happened, I just call the ring buffer short puke, and out on your standard error comes like, yeah, blah, here's the bump, here's the dump, right? Okay. Tools is unfortunately easy because I don't have a lot to say. I have tried tools. I've watched tools for a long time, like 20 years. And the answer is most of the tools either don't scale or they require 10x slowdowns and have high false positive rates, or they require PhD to use or some combination of the above. And instead what happens with tools is you have experts who you can rent to go help you use their tool. The tool's free, the expert is expensive. You call the consulting firm, they bring in the PhD for you. If you're a big project house and you have a lot of money for a big engineering team, you can grow an in-house expert that uses one of these tools reasonably well. But for sort of a standard development practice where I don't have a lot of people for the job I'm trying to do, don't necessarily have a lot of money to throw at a big ass tool to go solve this problem. The one exception I can say is find bugs. And I'm not going to commercialize find bugs. Go find it. You Google, you'll find them. There's a commercial variant. I know it scales to huge scale because Google uses it in house. It uses simple pattern matching and therefore only finds common bugs. But the common cold is called the common cold for a reason. It's common. Okay, common bugs are common, and so it finds common bugs. Yeah. It's very useful for finding stupid shit that's actually real that you didn't find any other way. You can bake it into your QA. I'll talk about it in the QA section here. You can bake it into your build practices and stuff, your continuous integration. Fine. Okay, here's a couple other stupid tricks I've used individually on one-off cases here and there. Defensive locking, this is where I think I don't need a lock. I'm not supposed to need a lock. It appears that I might need a lock. I don't understand why, so I lock it. If I did not need a lock and there is no contention, the cost of the lock is actually pretty cheap these days. It's a dozen or 2 dozen clock cycles on a modern x86 to take a lock that does not ever get contended. If instead it is contended and I got a lock and I don't understand why I have contention here and I'm trying to figure out why this should require a lock, then I can do a trick where I say I'm going to do a half a lock. And half a lock is to do a try lock, set a bit somewhere saying I took the lock fakely, I wasn't supposed to need one, and then unlock right away. And then on exit, test to make sure nobody else tried to do the same lock. And then if there's another thread comes in and he wants to take the same try lock and he fails, he'll recognize that somebody else is locking it. And I can get a stack trace for both the readers and the writers thrown in the debugger at the time of the crash for them both with this hack, right? I don't think there should be a lock here. I don't understand why there is. I'll get the caught in the debugger, both the reader and the writer, where the writer was in it on exit, he detects, and the reader's trying to get in on entry, he detects, and I'm stopped in the debugger. Very useful for debugging it. So it doesn't always work, but when it works, it works pretty well. Yeah. A couple other techniques. People have talked about formal proofs. Hardware guys use them all the time. I haven't seen it ready for prime time on the software side. I've tried several times. I do some really cool stuff with state machine-based programming for super low latency, high speed things, not general purpose by any means. I've seen people do statistical testing where they have some fails at a certain rate, and then they can puzzle through what kinds of things happen at that kind of a rate, and that narrows down the search base. I myself built a bunch of homegrown tools. They have the same problem as the other tools. They have 10x, 20x slowdowns or require PhD to use. I can talk to you about them offline if you want and go into detail what they're doing. They work. It's great when it works. But like I said, expert or giant slowdown or both. Okay. So that sort of ends the debugging individuals. Let me go talk now about QA and testing, which is bulk scale looking at how to find bugs. So there's a bunch of thinking changes that have to happen on the QA side when you're looking at testing concurrent code. And in particular, of course, it's not deterministic. You cannot cover the state space coverage by any remote means. I say less than 1%. Oh, minutest fraction of state space coverage can be covered using normal testing. You have the Heisenberg problem where the bug goes away as you sort of narrow in and try to log and test on it. You get different results. If you change the hardware, you change the memory size, you change load, any number of things change that sequentially it'll still happen and concurrently it will not happen. Okay, you get new failure modes: deadlock, live lock, missed signals and notifies, synchronization, atomicity failures, data races, performance failures. Why are you writing concurrent code? Because you want things to run faster or with lower latency. It didn't run faster. What happened? Now you got performance spikes, right? Probabilistic failures all the time. So one of the main things, the defensive per project ways to go out of here, is you need to split out your concurrent algorithm from your application logic. And we talked about this earlier. You want to test your application logic generally in a kind of a single threaded way. It's complicated enough. It does something fancy. I'm writing some cool game that my dude's jumping around, shit's moving everywhere, but I need to test certain application things single threaded. Break that out from the concurrent algorithm, which needs to have a concurrent based style of testing. It's a very different style of testing. There's a bunch of issues here we're going to cover through on how to make this go. And in particular, while the goal of QA you might think is to find the bugs, it can't. It's impossible. So you're really increasing your confidence that you're not just going to fall over and die when you hit production, right? And so I'm going to go after a couple different approaches for concurrent. Many of them work great for single-threaded normal coding as well, but they're important, more important on the concurrent side. Careful education, careful code reviews, education training on, this is exactly education training, some static analysis baking into your process, and then a bunch of stuff I'm going to talk about unit testing. There's some cool things there we're going to get to in a second. So absence of evidence is not evidence of absence. I didn't get it in testing, therefore it's not there. Doesn't happen for these things because they're rare probabilistic failures. You try to make them less rare with good testing, but it doesn't always work. So I do a bunch of these things all at once, and anytime I do a concurrent project, because the combination beats doing the individuals. So code reviews we talked about before. This is visual inspection, but as a team-wide thing, do code reviews. I strongly recommend it. Basically, all bugs are shallow to somebody's eyes, just not yours. In particular, the author of the code has a hard time looking at his own bugs because he knows what it's supposed to do and not what it actually does. And in general, just improves quality and buy-in from people. And if you're not doing it, requires a culture shift to get to the egoless, take criticism from your peers. It can be difficult, totally worth it. If you're not doing it now, I strongly recommend you look at doing it. Fine. Static analysis, we talked about it. Highly automatable, that's the main takeaway here. You can throw it into your standard build test environment, even pre-push testing, post bigger runs of find bugs and post testing. You'll get a bunch of false positives in the beginning. You can plan on dealing with them. There's easy ways to filter and ignore them and beat them down to where, the delta of new bugs shows up as the interesting thing. Fine. Also, annotations are very helpful, both for find bugs and for humans. So if you have a concurrent algorithm, start using annotations to dictate, and here I have a concurrent algorithm, and here's the lock, and here's the field that's supposed to lock, and here's how it's supposed to work, and shit like that. Fine. Okay, unit testing. So this is where you start to get a little bit more concrete here. Basic safety and liveness is what a unit test is about. I did an X, can I do a Y? But then I want to do 10 X's in parallel. Do 10 Ys work? If they don't, I probably have quick and easy deadlock concurrency testing, shows up on my desktop easily. Then I do load testing, do a million X's in parallel. Do a million Ys also work? Because by the time I do a million things, it's JITted. It's running a lot more often and a lot faster. I get a lot more interleaving opportunities for fails shows up. A lot of rare timing events now show that things are only 1 in a million, but if I run it a million times, it happens on me. Fine. Some framework test issues. So typical test harnesses have an issue with blocking algorithms. So here I have a bounded blocking queue I want to test. I've set it of size 1. I want to test what happens when the queue gets full. So I put something ABC in it. It's now full. I put a DEF. It's supposed to block. Well, that blocked my test harness. So the test harness just blocked here, never completed testing. So I didn't get to the following code. Fine. Exceptions and threads are ignored by default in Java. So on example 2, I make a new guy, I do a put on him, I launch another thread tries to take something out because it's a concurrent algorithm, it should take something out. He takes out something, he fails his assertion because it's the wrong thing he took out. He throws an exception, the join ignores the exception, silently the test completes. This one's worse than the first one. The first one just halted and stopped, stuck. The second one silently accepts when you actually have a failure. So that one's much more insidious. The test claims it passes when it failed. Okay, for these kinds of things, I use a white box testing that I sometimes call clock testing or tick-tock testing. And I'm going to force a controlled interleaving where I'm going to take my threads and walk them through one at a time at a particular order. And in particular, because I'm blocking and ordering, I can go debugging speed, where I can stop in the debugger and stare. Whereas if I used sleep, the sleep would time out and then I wouldn't get it in the debugger. And in fact, the sleep will time out if I have a heavily loaded QA testing box. The sleep may be not long enough and it may be too long in other instances, and sleep doesn't work well. So don't use sleep. Talk about it in a second here. Okay, so how do I do this? I make an internal clock, which one thread ticks and one thread talks, put some hooks in the test, and I can walk it through and force narrow races to happen. So here's some example, just a second. So there's a global clock. The players take turns. Thread 1 wants to know that he can put something in and then block because it's full. And then thread 2 is going to pull out. And he wants to know that the queue was full. He didn't block waiting for it. He blocked because it was full, that kind of thing. So thread 1 racily tries to do a put. Thread 2 immediately blocks by waiting for thread 1 to hit the tick 1. Thread 1 then says, I got to tick, I found a 0, I went to tick 1, and I'm now blocking until I get told to go again. Thread 2 asserts he can get something. He now blocks, waiting for thread 1 to hit a 2. Thread 1 goes and plays a def in, and back and forth it goes. And I force them, ding dong, ding dong, ding dong, ding dong. If I have more than 2 guys, I have to say who goes next. So with 2 guys, they can just take turns. With 3 or 4 guys, you have to name who's the next guy in line to go. But I can force all kind of weird narrow races to happen directly, one at a time, exactly where I want them to, and see that it's doing the right thing on a one-off basis. Like I said before, you can't cover all possible schedules, but you can force cover certain individual schedules that you're very interested in. Okay, load testing. Let me talk a little bit about load testing. So I said, hey, run it 1,000,000 times on my desktop. That's great for certain kinds of testing, and you should do it, and it's easy and generally quick enough, right? Big data, batch processing, do 1,000,000 in a row. That's pretty reasonable. Highly unrealistic, though, for irregular computation, like you might get out of a web server or a database, any kind of database-related thing, where you need to test a mixture of types and timing, because it's not realistic to say, I have nothing, I now have 1,000,000 things, one after another, all of the same exact thing, and then nothing. Because in that instance, the 1,000,000 things are all exactly identical. All your caches work perfectly every time. There's no race on the cache. There's no further updates to the cache other than the first one. Then you get 1,000,000 hits in the cache, and that kind of thing goes on. It's very unrealistic. Okay, the other thing going on with this one, like the curl example here, is that the server only sees one event at a time, and the load only hands him one event and waits until that event completes before he hands the next load in. So the server never does overlapped concurrent parallel things. He only does them one at a time. So you have to get to a notion where you're firing off requests independent of when they return. So the fire off needs to happen with a reasonable distribution. And for web services, it's common that you want to use an exponential distribution. That's not one that scales infinitely. That's one where it's very spiky. You can go look up exponential on Wiki, what the hell it is. Fine. It's a distribution that's not infinite. But it's definitely not flat and perfectly uniform. It's bursty. Okay. And because it's bursty, your server has multiple requests coming in faster than it can respond to. Because it's faster than it can respond to, he runs work in parallel now. And so instead of saying the work is I do, and then I did, and I send a response, and then I get a new work, but I'm not doing the old one because it's done, and a new one back. No, instead they're overlap. And now the work is running concurrently. I'm testing my locking. I'm testing my concurrent access. I'm testing my cache updates while other threads are reading. That kind of thing are going on. Gil Tene did some great work here. I encourage you to go read his work. I haven't looked at it in the last year or 2, but as of a couple of years ago, it was still the best state-of-the-art work I've ever seen on concurrent load testing and how people typically screw it up, and typically screw up the measurements that come out of concurrent load testing because they're measuring the wrong thing. Fine. I'll let you go read Gil's work on that. That's a whole nother talk all to itself. The other thing I see people do is have a lab versus production environments where the production is making all the money. So it has all the gear. It has the full speed network, has a full speed database. It's been incrementally grown as the load of the clients have grown, and it's now doing all the right things and making all your money. And the lab is what the guys did when they didn't have all the right things that they could do off to the side. And so it's highly unrealistic. And it is unrealistic. Because it's unrealistic, the production guys don't want to take the lab code because it hasn't been tested realistically. Fine. As soon as they try to take it, it fails because they can't test realistically. Totally worth the dollars to get a smoother lab production workflow. You need to have, in fact, a much better answer here is to have 2 full-size production workflows, and you flip them on a regular basis, hardcore, force the flip. And if you don't have something useful out of the lab, folks, you roll it back to the last one, but you do the flip. Because you're doing the flip once a week, you're used to it and you know how it works and you know the flip is stable and sane, and you decide at the time of the week boundary that I'm going to take the new lab thing or I'm not. Right? Fine. Statistical testing. So this one's maybe a little more unusual for folks who haven't seen this. You see a fail in testing. It's hard to repeat. I can't get it to fail my desktop. Can't get failed to debugger, whatever. Fine. So I'm going to use the same solution as the hardware guys when they solve a problem that's the same kind of problem. You defeat randomness with statistics. You repeat until, and you count the failure rate. You want to get a dedicated machine. You want to run the problem over and over and over again under heavy load, and you don't want to catch the bug. You want to count the fails. So every time you catch the bug, you blow the server down and you restart it and you go again. But you count the fails. Maybe get a log file, maybe not. Be quick and cheap and go again. And you want to see the failure rate. What you're trying to do here is get a guaranteed fail box. And you discover that what X is to guarantee a fail. So if X is I need 1,000 runs and I made a fix and I ran it once, I can know that I had no way to know whether I fixed the bug or not because it only failed 1 in 1,000 anyhow, right? So I need to have a way to say I have to run it X and then I see the fail reliably because now I know when I come with a bug fix, I actually got a bug fix or I just got lucky, right? So the next thing happens here is I can detect changes in the failure rate because what usually happens is the bug's tricky. I'm having trouble finding it because only 1 in 1,000. Fine. I started adding logging and printing and logging and printing. As I get closer and closer to the bug, I'm changing important timing. As I change the important timing, the failure rate changes. And if the failure rate starts to drop off, I'm getting close. But if I'm not changing the failure rate and I'm not otherwise seeing changes in the bug behavior, I'm probably not logging near the right place. I'm missing where the bug is. I need to think again, right? So basically, it lets me zero in on the bug. Furthermore, once you're here, you probably have several bugs that are interlocked. Otherwise, you would have found them a long time ago because if just one, that was always easy. You usually have a confusion of low frequency bugs happening, and different ones are popping at different times. So as you kind of narrow down timing on things, you push different bugs to popping up to be important or not, and it waffles back and forth, and suddenly you like figure one out and you home in on it pretty quickly and you get it, and you go back to the main box, and now you can run and see your timing has changed, but you still get a failure rate. Totally, unfortunately expected. But you have the statistical significance that shows you that it fails now at 1 in 2,000 instead of 1 in 1,000, you can go again. Fine. The general rule here is probabilistic events require many runs, and you track them with statistics. Same as the hardware guys do. Okay, distributed. A little short thing on distributed here. Much of the parallel advice applies. I did this on distributed. I built a cluster computing software company. Replaced data race in a shared memory with a network race in a shared cluster. Replaced how many threads with how many nodes. And 5 is a good start. And where did I come up with 5? If you have 1 node, you ain't got nothing distributed. If you got 2, they take their turns. It's too easy. If you got 3, you have some edge cases and a man in the middle, but it's too common that he's not really in the middle. When you get to 5, there's often a thing where somebody's the center and somebody's an edge and somebody's really in the middle between the center and edge. You get more cases. So I kind of found that 5 was a good enough number, and I could run it on my 1 physical machine with 5 processes or 5 virtual boxes. And that was a useful testing place. And unfortunately, of course, network costs get really low if you're running them as virtual boxes on the same real hardware. So you have to test with real network latencies, which you can fake up to a point by injecting failures and sleeps and timing. And that will test things like dropped or duped UDP packet things of doing, remote gaming things, broken TCP connections and retry logic. All needs to get tested, but until you test with the real network and the real latencies, you don't actually get a robust test yet. But you can go a long ways on your desktop by just injecting network failures and network delays and having multiple processes or multiple virtual boxes clustering themselves. Also, the other things I talked about for concurrent algorithms work distributed as well. Statistical testing, load testing, cheaper printing. I've done all of these things in a clustered computing environment, and they all were successful in their various ways. So that's it. Wrap it up here really quick. Anti-patterns. Okay, we've all heard about double check locking, you need the volatile, but the other real anti-pattern here is using accessors to hide your concurrent algorithm because you like the business logic of it, but then you can't see the bug because it's hidden by the accessors. And the usual bug is two readers with a rare null writer in the middle. Sometimes the writer's not a null and it's still buggy, but it happens. One I didn't talk about, but it's the same kind of thing, is using a concurrent safe collection like concurrent HashMap, but using two non-thread safe calls. So here I have get something from the cache, and if I don't have it, compute it the expensive hard way, put it in the cache so next time I get it. Sounds great. If I have two threads race in to go get from the cache and they both tie and they both get a null out, then they both compute it. Okay, they make two of them and they both jam them into the cache. Now the cache is concurrent safe, so it takes the two writes just fine. But the second write, the first write got thrown away because the second write overwrote it. Then both guys think they have the one true copy of temp. They both mutate the one true copy of temp doing what they're doing with it. And they think their results are permanent because they're in the cache, but they're not permanent because there are two different temps and one got dropped. And so they lose an initial modification the first time that temp got made. Fine. So the big moral here is that you're often hide your data race by good programming practices, writing. You're solving some hard, complicated problem, and you're trying to write accessors to put meaning to the hard problem around, abstractions around the underlying data fields. Fine. But you need more speed, so you reached for concurrency in multiple threads, and you end up adding concurrency to a large, complicated problem without realizing that concurrency is its own complicated problem. It needs different kinds of wrappers, different kinds of access control and testing. It's very difficult to design an API to concurrent algorithms after the fact. So it's not really a bolt-on kind of feature, although people commonly do it that way. And when I talk to people who've done data race bugs and had issues, they start out thinking they know what's going on, and after a while we figure out they don't. And they don't know which thread can touch what or when or where. And they're always surprised by the interleaving that triggers the bug. And that's sort of a truism that's stupid. Because if you weren't surprised by it, you would have looked for it. And then you would have solved the bug and fixed it. But you didn't think about it. And there's way too many interleavings to think about them all. So it just slid by you and like, oh, yeah, I guess that could happen. And suddenly, bam, you got the bug. But you lived with it forever, however long. So best answer, well, don't go there if you can avoid it. So immutable works, but it's very specific and very tricky to apply. It doesn't apply everywhere. Private data obviously is not really concurrent. Yeah, great. Use well-tested Java util concurrency. But when you have to go here, admit there's dragons and start out thinking ahead of time. Okay, I'm going to do concurrent algorithm. Document, record where and when I think things are going to be concurrent and why. And you design the code that way as you go. And that's Q&A time.
Thank you so much, Cliff. That was an excellent presentation, full of great takeaways, and I feel like it's really worth watching it a couple of times to not to miss any of the great hands-on pieces of advice. And that's really great. We got one comment which says great content. Which is confirming my statement. So thank you so much. We don't have any questions in the chat. It's still time to ask some questions if anyone wants to ask a question. I have one question. This was slightly covered, like you were mentioning that logging is bad because it kind of allocates, it reorders things, and they slow down.
It changes timing,
yeah, confuses timing. And how about the async loggers, like they are getting popular right now, and why aren't they? Or let me not answer the question by asking it, but are they a good example or like a good thing to solve the issues that you're mentioning, or not really?
So what did you call it? Async loggers?
Async, so asynchronous loggers.
I haven't looked at them individually. That's okay. The right notion. It all comes down to quality of implementation.
Yeah.
So asynchronous removes some amount of overheads, the blocking between each other and the blocking to a serialized IO stream. The issue there is if you have high volume, my cheaper printing solution can support billions of updates a second without changing timing. That's a hard number to reach. Certainly tens of millions to hundreds of millions is I have done reliably and got it to work fine. So maybe you don't need that level. And when they say async, I don't know if they're ordering between threads or not eventually. So one of my points here is I don't order between the threads until I crash. But then I order because I stopped at the crash and said, okay, gather all the threads and do a big sort and, and gather all the threads. That's an ordering operation. Stop everybody. Quit writing to your logging because you'll overrun your ring buffer and you'll lose it, right? So there's a big halt everybody, and then there's go, sort it. And the halt can be, it crashes in the debugger, and the debugger just halted everybody. And then inside the debugger, I say, oh, go call the print function, which gathers all threads and prints. If the async guys are doing the same kind of thing, it's the right notion. They got to keep the cost down. That's the main trick. Keep the cost down. One of the secret hidden failures is that if you say logging, where I said, quote, and here I crashed because plus bar X is greater than plus quote Y is blah, 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 blah. And as soon as you do a bunch of pluses in there, you made a bunch of string math, which goes to string builder and buffers under the hood, and you do a bunch of allocation. And that's your main cost. That's your slowdown right there. That's already getting to not just hundreds, thousands, can be tens of thousands of clock cycles pretty quick. Any narrow race, you'll start to hide it. So you can't do strings. But the APIs for the usual logging thing encourage you to do a lot of stringy things. You have to tread lightly there, and maybe the logger guys have a version that takes only ints, and they slap it down a time. You can do this the right way. You can make a logger for this. I just don't have it in front of me to do a quality check on what you're talking about.
Yeah, sure. Thanks. That's still very helpful. Okay, so I think it's time to wrap up. Thank you so much one more time, Cliff. It was a great gist of what we can expect. What the participants of Masterclass can expect when next month. It starts in a couple of days, so we're really looking forward to it. Let me just say goodbye to the participants in Polish also, and thank you so much one more time, Cliff. Dziękujemy bardzo za wzięcie udziału w tym webinarze. Myślę, że był to znakomity przykład tego, czego możemy oczekiwać po No Fluff Jobs Masterclass, czyli naprawdę hardkorowej wiedzy podanej w przystępny sposób, która po takim wykładzie podnosi nasze umiejętności bardzo, bardzo wyraźnie. Także zachęcam do obejrzenia nagrania z tego webinaru. Będzie dostępny online w dniu jutrzejszym i zapraszamy wszystkich do No Fluff Jobs Masterclass. Przypominam o 20% zniżce dla wszystkich uczestników webinaru. Pozdrawiam serdecznie. Do zobaczenia.